But it really starts, this starts at the personal level with individual people in the PSP, making commitments to their team, and then above that, the team making commitments to the business, and so on. The other big idea, obviously, is to learn from experience. The lovely quote from Deming, "In God we trust, all others must bring data," I really, really like. So it's about also, as we get into PSP, we build a body of data about our own personal performance that says I underestimate by this much habitually, or I overestimate my work by this much. And we end up with a database and some useful statistical analysis, which gives us the key to be able to actually estimate our future performance in a sensible way. The personal data eventually, firstly gets anonymized as soon as it leaves your desk. That's a very important principle of PSP. People's individual data is anonymized the moment it leaves their desk. It gets rolled up at team level. Hopefully the errors cancel out in a statistically useful way. And then at team level, the team is then able to make commitments and estimates and so on that we'd like to be able to see. And again, learn from its experience in the past. There are some basic measures. In software measurement, we talk about base measures for things. The base measures in PSP that we use when we're learning this, firstly, we need a measure of size. It might be size of a program, where a program, we talked earlier about lines of code, sometimes being a useful measure. It might not be lines of code. It might be function points, someone mentioned earlier. It might be nodes in a SCADE diagram, for example, or something like that if you're in a model-based environment. I don't mind what you measure, as long as it's something you can measure accurately and precisely. Accurate measure means if Andy and I measure the width of that desk, we both get the same answer using the same tape measure. Andy's not wildly off my measure, yeah? Precision means if we measure it over and over again, individually, our answers are off by a small standard deviation. So we wish to be able to measure things well. The other thing we measure very carefully in the PSP framework is defect rate, meaning every time you find that you've made a mistake and you have to go back and rework something, you go, and you write it down or you notate it somehow to say, I've made a mistake. You have to go back and work out where you introduced the bug or the defect. That's really important, the root cause analysis to say, well, this mistake was introduced yesterday or a month ago or a year ago is very important, because knowing the gap between the introduction and the removal of a defect is incredibly strong piece of information to have, because the width of the gap usually correlates with how much it's going to cost you to fix a thing. So that's very important to go back and look where things were introduced. We record the type of a defect. Is it a syntax error, a semantic error, a logical error? In programming, you could come up with some taxonomy of defects. That's very useful, because then you can learn if you personally are prone to making a particular type of defect. If you discover that, then you can do something about it, and so on. At a team level, you might discover that the team are letting some particular type of defect through into testing, and that's costing a lot of money. And at the team level, you can take steps to do something about that by introducing some earlier phase. And how long to fix? Well, clearly, we're looking for that, because that tells us how much it's costing us to rework these things, and that's terribly important to build a body of evidence. Without that data, it's very hard to justify improving. I don't know how many of you have been involved with process improvement programs within your companies within a framework like CMMI or Six Sigma. It's very hard to justify process improvement if you haven't got any data. If you can't go to your boss and say, boss, we want to invest £100,000 in process improvement, and the boss says, great, how much will we save? And you say, oh, we don't know. It's really difficult to get your boss to spend the money if you really don't have any idea of how much you stand to gain and the return you're going to get from that investment. We measure consistently. Okay, that means everybody on the team measures the same thing in the same way. There's no point having one person on the team measuring function points and another person measuring lines of code, because they're not going to add up when you roll up the data. So we need everybody to agree on what we're measuring. That's basic stuff. And finally, we look for correlation between the data sets to judge its usefulness for predicting future performance. So particularly with a size measure, I'm looking for correlation with effort. If I find that my number of lines of code in no way relates to how long it takes me to produce that code, then measuring lines of code probably isn't useful for predicting my future performance. So that's probably not a good measure. You have to go and find a measure that is useful. And we use the basic notion of statistical correlation to find measures that are useful in that sense. There's some other basic elements to it. It's very big on the use of scripts and checklists. A script is a process description on one page of paper. It's just like a little chart that says, here are your entry criteria. You know, to execute program design, you must have the following. And it will say, you know, requirements or something like that. So there are entry criteria clearly stated. There's a list of steps that says you must remember to do this and this and this and this and this. It's incredibly powerful, not just reminding you to do certain things. And finally, there are exit criteria saying you are supposed, you know when you've finished, when you've produced the following things. And finally, there's what we call a post-mortem on every script. The post-mortem is where you stop and take a breather and say, okay, what went well? What went badly? How many mistakes did I make? What could I have improved? That's your process improvement step, and that's actually planned. You plan to spend a certain percentage of your time doing your root cause analysis and your process improvement stuff. And it's not forgotten. It becomes mandatory as part of the script, really. Forms are just blank pieces of paper with spaces, or semi-blank pieces of paper, where there are spaces to fill in data. So there are just structured forms for filling in data. Again, they've proved incredibly useful. And checklists. Checklists are literally just things saying, like when we're doing code review, we have a code review checklist that says, you must check the following things in this order, this, you know, whatever, bum, 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 bum. Checklists are incredibly powerful. Andy and I have just read a book called The Checklist Manifesto. I don't know if any of you come across it, by a guy called Atul Gawande, who's a surgeon. He's a surgeon in Boston. And the use of checklists in surgery, it transpires, has made an enormous difference to safety of basic surgical procedure in hospitals. And the World Health Organization now is promoting the use of these very basic checklists, saying things like, have you remembered to give the patient just the right level of antibiotic at a certain time before the first incision is made in the patient? Turns out that's really important when you're doing surgery, that you get the antibiotic just at the right time. And sometimes that goes wrong. They give you the antibiotic, some emergency happens and the patient doesn't get seen to, and then the antibiotic's worn off or something. So just these basic checklists. And the other obvious example is pilots. In flying aircraft, pilots have checklists. You know, everything you have to do just so before you're allowed to taxi the aircraft or whatever. These are very, very powerful, and their use in software engineering seems to be very, very good as well. This all might seem quite familiar. You might say, hey, this is all old stuff, and it is. Watts Humphrey developed a lot of these ideas in the late 1960s, because he managed the OS 360 project. Perhaps for some of the older members of the audience, I don't know if any of you remember OS 360 on the IBM generation, that generation of IBM hardware, but Watts was the manager, the boss of the OS 360 effort, and he developed a lot of these ideas in the late 60s. So this is not kind of wow, new stuff, but actually doing it properly is the really novel thing about this process, I guess. Here's an important point. The PSP training and the whole scheme is entirely technology neutral. It doesn't say you have to use this programming language or whatever. It doesn't say anything about technology or verification tooling or anything like that at all. So when I took the training, there was me using Spark, obviously, and there were other guys, other people on the course, some using C++, C, PHP, one guy on the course, somebody using VB, a couple of people using Java. They've had someone do it with SQL, for goodness sake, as a programming language, would you believe? So they've had over 1,000 people through this training course using a wide variety of technologies and languages, and it's fine in that regard. That sort of, I guess, broadens its appeal, because you can teach this to pretty much anybody who claims they can program in any language. That's good, because it broadens its appeal. But as a result, we found some of the things we've been doing, particularly with our background in safety-related systems, some of the stuff we've been doing, like using really well-defined language subsets, using strong static analysis tools, had completely missed the guys at the SEI. They weren't aware of what had been going on in the safety-related community over the last decade or so. So that was an interesting observation.